So in the last video, we figured out how to solve the projectile motion of this example. We said we had a person standing up on a cliff 50 meters high. They threw a ball at 20 meters per second at an angle of 30 degrees from horizontal, and we figured out that flight path. By the way, here's the graph laid over our original diagram here. How cool is that? I couldn't resist. Now in this one, I want to figure out an example where we assign a mass to this ball, and then we figure out the actual kinetic energy and potential energy and graph that as well. So here's kind of where we left off. We had our graph that we figured out how to graph the entire flight path, and then we can change anything in here and the graph will update automatically, and it'll always end at 0 thanks to some calculations that we built into this. Now, like I said, we want to add in some columns. So how will we do that? Let me just kind of clean things up first of all. So what we want to do is add some columns here, and we'll add the velocity in the x direction, the velocity in the y direction, and let's just solve those for now. I'm going to switch this back to 50 meters just so our graph looks right. So if you remember, we are solving this considering, or not considering, air resistance. So the velocity in the x direction is going to be constant. It's not going to slow down over time. So the x component of this velocity vector at that 30-degree angle is never going to change. So what we can do is just say equals, and then select our initial x velocity there, lock it, hit enter, and then that'll populate down. Then for the y velocity, we need to do a little bit more of a calculation. We need to say our initial y velocity, lock that, plus gravity, lock that, times our time. So we can see that velocity is decreasing by 9.8 meters per second squared. So every second that velocity is decreasing 9.8 meters per second. So if we look at 1 second, it decreased roughly 9.8, and that the reason that it's not exactly 0.2 is because of a rounding error. So if I increase that, you can see that's not exactly 1 second. Let's figure out how much kinetic and potential energy is in the ball at any given second along the flight path. So in order to do that, let's type in PE and KE. So this would be our potential energy and our kinetic energy. So the equation for potential energy is going to be, draw over here on the right, potential energy equals mass times gravity times the height of the object from the ground. And kinetic energy is going to equal 1/2, oh my gosh, 1/2 the mass times the velocity squared. So now that we know that, we can calculate both of those at any given point. So to calculate the potential energy, well, first of all, we're going to need a mass. So let's just drop that in here. I'm going to right click, insert, shift cells down. Okay, so our mass, let's assign that a mass of 5 kilograms. And so now we can use that to calculate the potential energy. So we take our 5 kilogram mass, lock that, times our gravity, lock that, times our height, and our height is going to be our y value. So the distance our ball is from the ground is going to allow us to calculate the potential energy that's in that ball at any given point through this flight path. So if we hit enter there, that calculates, and this is giving us a negative value because our gravity is negative, so we'll just put absolute value in front of that. So we can already see that our potential energy starts at this number, 2,450 joules, that would be in, and then it slowly increases as the height of the ball increases, and then it starts to come back down as the ball comes back down. And the interesting thing is that the kinetic energy will actually do the exact opposite. So the kinetic energy is going to start higher and then go down as the ball slows down toward the peak of the arch, and then it will increase as the ball accelerates back toward the ground. So let's see what that looks like. So we're gonna do 0.5 times, again, the mass of our ball, lock that, times our velocity squared. So actually what we need to do is go square root of the velocity in the x squared plus the velocity, plus the velocity in the y squared, and that will all be squared as well. So we'll go, there we go. So if we were to add yet another column, just say total energy, and we're going to say that equals this plus this. We can see that it's equal all the way through, and that's actually the conservation of energy, the law of conservation of energy, saying that the potential energy plus the kinetic energy of an object, no matter what the velocity, the height, the acceleration, all that always has to be equal. So that's pretty cool. Now what we can do is, let's just grab all this and insert a graph, and it'll just be a nice visual. And I only grab the whole thing because it's the easiest way to do that. And then, whoops, right there, hit enter. So that is a graph comparing our potential energy and our kinetic energy over time. So just another cool visual to help understand some of these kind of complex topics. If I just zoom out here and I change some of our variables, again, let's say 100 meters, and let's go 60 degrees, and this is where it'll get you can see our graphs update. So let's say 0. That'll change it a lot. So we can see now our potential energy when the ball is sitting on the ground right at 0 seconds. So the moment it's launched, the potential energy there is 0 because the ball can't be accelerated. It can't be moved downward at that exact point. It has nowhere to go. But the kinetic energy, because it's just been accelerated in an absolute instant all the way up to our velocity, our initial velocity there, 20 meters per second, the kinetic energy at that point is all the way up to 1,000 or 10,000 joules. And then as the ball goes through its flight path, right at the peak here, we can see the potential energy maxes out and the kinetic energy is at a minimum. And what's important to note here is that the kinetic energy never reaches 0 because, and I'll switch to draw mode again to kind of explain this. I'll switch to draw mode here because even at the peak of the arch, when the ball is right here, it still has an x vector. There's no y velocity to it. So that's where the kinetic energy is lost and at its lowest, because there's no y velocity, but there is still an x velocity, so the kinetic energy will never reach zero through the flight path. Alright, I hope you all enjoyed that one. To get more videos as they are released, make sure to hit that subscribe button. If you like this video, make sure to like and share, and if you didn't like it, well, then leave me a comment and let me know how I can improve. Last but not least, this channel is for you, so if you have any suggestions for topics you want me to cover, make sure to let me know. Thanks for watching. We'll see you next time.